Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Great to have you back. We're now going to start diving deeply into technical aspects of astronomy and how they relate to the physics of astrophysics. So to this time, we're going to be talking about the nature of stellar brightness and luminosity distances. So let's start with the concept of what we mean when we say the words, how bright is the star? Usually when I take people outside and go to a telescope, they're going to say, wow, look at that bright star. What they won't say, look how bright that star is. They'll say, look how big that star is. And people mean big, but they really mean bright. And so what do we actually mean by the word bright? And so brightness is a thing that we actually try to quantify. Brightness is an amount of energy we receive in terms of photons per second at given brightnesses. And so that can over in a detector, such as an eye or a camera or something like that. So when we talk about that, we're really talking about the nature of brightness is a perception. But really, if we want to know about the nature of the object itself, we need to talk about luminosity. And luminosity is the intrinsic amount of energy the object, such as a star, is putting out every second over whatever wavelength band we wish to care about. So how bright is a luminous source? How bright is it? Well, that's the number of photons that arrive at a detector. And so that's what we call the apparent brightness. And frequently in the literature, we call that B. Capital big B is the apparent brightness. And what we measure that in is some really odd units, but strictly speaking, everything that we ever measure brightness in is essentially either photons per second in a surface area or energy per second in a surface area. Photons per second, we already know what the energy of the photons is, so we can just deal with that. So our real question is we want to know the energy that we're receiving per second over a surface area, and that's what we call the apparent brightness. The thing we're trying to hunt for, though, is what we call the luminosity. That's how bright something really is. So we're getting these two words, brightness and luminosity, a little mixed up, but we're going to resolve that shortly. Luminosity is the entire luminous output of the star. When we say luminous output, that's where it comes from. Luminous means light. So luminous output is the total amount of energy output by a star in the form of light per second. Now, we can measure that in energy per second, or more commonly, we use the word watts, such as light bulbs. Light bulbs have a 100-watt light bulb or a 500-watt light bulb, et cetera, et cetera. The sun's a lot brighter than the average light bulb. So the units we measure luminosity in are energy per second, and that's what the production amount of energy is happening by that object. So these two things are, of course, related. Because brightness is how bright you see it to be, and luminosity is what it's actually putting out. And how bright it appears to you is actually depends on the luminosity divided by 4 pi times the distance to the object squared. Because let's assume that the light is being spread out uniformly across a sphere, such as like a bulb light. So if it's a bulb light, we expect it to be going across a sphere, and so it spreads out evenly, and so the brightness drops off as the distance squared to the object. So the luminosity gets dimmed by the distance squared. So that's where we get the units of energy per second per square meter, or watts per square meter if we're using SI standard units. And when we're talking about that, that's where that 4 pi comes in from. It's not just the distance squared, it's the 4 pi because it gets spread out over a surface area and it drops as it goes. So if something's twice as far, it's 4 times as dim. If it's 3 times as far, it's 9 times as dim. If it's 5 times as far, it's 25 times as dim. If it's 11 times as far, it's 121 times as dim, and so on. So the 4 pi comes from the fact that we're assuming it spreads out evenly over the surface of a sphere. So what do we mean? Does the star look bright simply because it is intrinsically very luminous, or is it faint but nearby? So we have to measure the distances to things. So distances become a very important thing. Luminosity is not distance dependent. It is a distance independent property. It's a property of the object itself, whereas brightness is dependent upon our perception of it. So we need to be able to know how to measure brightness, and that science is the thing we call photometry. And we express that photometry is literally the measuring of photons, photometry, the measuring of photons. So we're counting the total number of photons we receive. And there's a couple of ways we talk about it. We can express it in terms of the old familiar thing that we learned from Hipparchus a long time ago in stellar magnitudes, or we can express it in absolute fluxes, meaning the energy that we receive in the detector per second on top of the surface area. And in astronomy, we use both of them interchangeably. So the magnitude system is something that you'll hear very commonly if you go outside with a bunch of amateur astronomers and say, oh, up in the sky, that's a 5th magnitude star. Or, this is a great night. We can see down to 6th magnitude. And you'll hear things like that. Or, wow, the brightest star in the sky is a 0th magnitude star. And you'll hear such things. Well, the tradition of magnitudes dates a very long time ago. It comes from Hipparchus, which was a Greek philosopher, and he actually of Nicaea, and he lived roughly in the 2nd century BC. He lived about 190 BC to 120, and he classified stars and ranked them into magnitudes. He said the first magnitude stars are the brightest, the second magnitude stars are the second brightest, and the other ones are dimmer than that. So he ranked them into 3 groups. Later on, Ptolemy of the Almagest, who gave us the Ptolemaic system of the cosmos, which is the sun-centered, Ptolemy came along and made it more qualitative and added them into 6 separate buckets so that the magnitudes could be divided in the first magnitude being right all the way down to the sixth brightest stars, 6th magnitude being the sixth brightest type of stars. So these were all relative brightnesses, and they were done by eye. There's no detectors, there's no photometric detectors, no cameras in 100 BC. So that was kind of a tricky thing. So you had to say, well, this one's a little bit brighter than that one, this one's brighter than that one, that one's brighter than this one's brighter than that one. So they ranked them in terms of their apparent brightness. And that was called their magnitude system. And magnitude simply meant to them, it looked bigger, because magnitude means size. So my goodness, it's actually not a size thing. Stars are so far away that we can't actually perceive their size from Earth very easily. Only a few stars have actually been measured in such a way. But the point is that magnitude means size, but here we're using it as the word for brightness. And magnitudes are a measure of relative brightnesses between stars. Now, the modern magnitude system was developed in 1856 by Norman Pogson. And Norman Pogson at Oxford, who was who's considered to be, went to India, I believe he was from India originally, and he developed what we call the modern system magnitudes. And he codified this ancient idea of Hipparchus into a separate set of definitions. He said, well, every 5 steps of the stars, every 5 magnitudes is a set of 100 brightness in times. Now, he actually was able to quantify this because it's very close to the truth in terms of the old idea. So Hipparchus' idea, modified by Ptolemy, was actually very close to the eye, and the eye acts logarithmically in terms of the brightnesses that we can measure. And so he said that if a difference in 5 magnitudes is 100 times brightness, and so he also said the standard star of brightness was Vega, which is 0th magnitude. So for example, a 9th magnitude star is 100 times brighter than a 4th magnitude star, and a 0th magnitude star is 100 times brighter than a 5th magnitude star, and so forth and so on. So the faintest stars that we can possibly discover with any aspect aren't really necessarily stars, they're probably galaxies or quasars. That's about 30th magnitude, and those have been detected by the Hubble Space Telescope. Ground-based equipment, the best ground-based equipment by amateurs is roughly in the order of 15th, 16th, maybe 18th or 19th magnitude on the ground. So you can get some pretty faint stuff. Remember, every difference of 5 is 100 times. So 0 magnitude is 100 times brighter than 5, which is 100 times brighter than 10, which is 100 times brighter than 15, which is 100 times brighter than 20. So a difference between 0th magnitude and 20th magnitude is 100 times 100 times 100 times 100, or 10 to the 8th. That's 100 million times brighter. A 0th magnitude star, such as Sirius in the sky, is 100 million times brighter than a 20th magnitude star. And there are 20th magnitude stars that have been observed in the Milky Way. They're just really dim and really far. All right, so Pogson's definition, it can be codified numerically by saying the ratio of the brightnesses equals 100 to the difference in magnitudes divided by 5. And so the difference in 5 magnitudes gives us 100 times brightness, and that allows us to define the magnitude system, but still it's a relative magnitude system. It's always relative. What's nice though is that it actually allows us to codify. If we can get the brightness in energy per second on a surface area, we get the brightness of one star. And then we can actually translate brightnesses between each other. This also allows us to roughly guess by eye the brightness of something and then allow us to get very close to what we actually get with some sort of formal detector. Nicely enough, the standard star is Vega, and Vega is prominent to most people in the sky. And the standard for Vega is a little tweaky because Vega is a variable star. But in terms of things, Vega was defined in many magnitude systems to be 0. And so you can basically start from Vega and go everywhere. And you compare and compare and compare. Oh, how bright am I compared to Vega? I'm brighter, I'm dimmer. I'm brighter, I'm dimmer. Vega is useful because it goes across the zenith for many North American and Northern European and Northern Hemisphere observers. Doesn't go across the zenith for people in the South Hemisphere, so they got to use secondary standards of some kind because the entire system has been centered around Northern Hemisphere. So we can codify that, and so basically we can say the star compared to Vega's brightness could be 100 to the stellar magnitude divided by 5. And that allows us to actually compare a star's brightness with respect to Vega and give us a numeric value. If somehow you can get the energy received per second at Vega, from Vega, as you can perceive energy per second on top of the surface area, that gives you that thing. Now, you can do that both ways because your detector detects in energy per second. That's how it detects. So you're going to translate this into magnitudes. So magnitudes tend to be a pretty handy system because they're something visual. Also, they're logarithmic. So therefore, the apparent magnitude system ranges from negative 30, which is roughly around the sun. The sun's a little bit dimmer than negative 30. But the apparent magnitude of the sun is negative 27. It goes all the way to the full moon, which is about negative 12.5 or so. Naked eye limit is about 6. Binoculars go down to about 10. The typical 1 meter scope is around magnitude 18 or 20, and anything bigger than the meter class scope, that's almost out of amateur astronomy land. There are some amateurs who have bigger scopes than this. There's not many of them. They're expensive equipment to use and work with. But then we're talking in terms of large scale observational qualities, and you get to 4 meter class scopes, which can observe down to 26 magnitude, and the Hubble that can observe to about 30th magnitude. So the science of flux photometry, and what we call flux, not the flux capacitor from Back to the Future, but flux photometry is the total amount of energy, meaning flux. Flux is another name for brightness, is the total flux that we perceive on top of it through a detector. Sometimes you wish to use fluence, where fluence is the total amount of energy, not just energy per second, but total energy on a detector. So it's energy per second, and that's been integrated over time. It would be called the fluence. So flux photometry says, I'm going to measure the brightnesses between various stars using various standards, and I'm going to use a filter wheel on top of this thing and check the differences in brightness between various filters. And then I'm going to start from Vega or whatever standard stars I have, perhaps anything in the Landolt set. And that'll send me over to brightnesses of stars. So the science of flux photometry then says, good, I'm going to try to get these brightnesses as accurately as I can, and I'm going to difference them against known standard stars, or if not Vega, then standard stars that are agreed by the entire astronomical community in order to say this is how bright a star is with respect to this. So these standard stars have had their energy output carefully measured and repeatedly measured for non-variability, so they can be called standard stars. And that's how Vega was discovered to be a variable star. It's a slightly variable star, so it's harder to use. The sun is a slightly variable star in terms of if you were looking at it from a great distance. In fact, it is a variable star. So we have to take into many accounts when we're doing the science of flux photometry. We have to detect whether or not there's clouds in the sky, how high the object is in the sky, there's a lot of things, the detector itself, how your camera works, how your telescope works, whether or not the readout of your camera is good or bad, the temperature of your system. There's a whole bunch of things that can affect the brightness of your measurement. So that's for another day, and I'll allow you to go dig around the internet to walk down that very deep rabbit hole to see what you have to do in order to calibrate to your telescope. But in very general terms, we can then say the luminosity of an object measured through some brightness. So is simply equal to 4 pi times the distance squared to the object times that brightness. And you just need two brightness, you need two measurements in order to get the actual luminosity. You need to know the distance and you need to know the brightness. So if you can get one of those, you can get two of those. Brightness is pretty easy. That's just what you get at your detector. But you've got to backplay it and remove all the effects of the Earth's atmosphere and many other effects in order to make sure that you actually get really what you think is the real brightness. So you can say, oh, there's all these things that took away light, darn it. And you take that into account, and then you will get the brightness outside your detector and outside the atmosphere. And then you get a distance measurement, and guess what? You'll have the luminosity. So a lot of practical issues associated with this. It's a huge number. The largest thing, I described many of them to you, but one of the biggest is distance. Distance, distance, distance. Oh, it's the worst thing in the world. But a lot of distances can be measured using parallax. And so parallax gets, by the Hipparcos satellite in the early 90s, got the distances to about 100,000 stars, and the Gaia mission recently got distances to over a few billion stars. So this is a big, big, big improvement. So using these distances will allow us to get secondary things, such as luminosities based upon appearances that can be seen without checking distance. So distances are incredibly critical, and once we get those things, there's a lot of things to go. And luckily, the Gaia mission has done a lot of that, so it's fantastic. So luminosity is either measured in watts or in this unitless thing that we will call absolute magnitudes. Absolute magnitudes, or luminosity in watts, they don't depend on the distance. Most stars have different absolute and apparent magnitudes, meaning the absolute magnitude is different than what we perceive it to be or see it to be. And the lower the number, the more luminous it is in magnitudes, right? And luminous just is how much light is coming out. So what we'll tend to do is we'll compare two objects' luminosities, and we see that they're relative to their brightness, and the inverse of their distance squared, and that'll give us what we're going for. But we can create this concept called the luminosity distance, meaning how far is it based on how bright it is. So let's take as our example the sun. We can measure the sun to a pretty good accuracy, a very good accuracy. It's roughly 93 million miles. That's a good accuracy, 150 million kilometers. So we can use that as a baseline. So if we know the distance to the sun, and if we know the luminosity of the sun, that's also very well studied. So if we got the luminosity of the sun, we've got the distance of the sun, we can make brightness measurements in the sun, then that helps us. Strictly speaking, we want to go across all wavelengths, and that would be called the bolometric luminosity, but we'll talk about that maybe later, but I don't think that's totally critical. But that's our real end result, is the total output. So we're going to assume that we're doing the bolometric luminosity. In any event, so you figure out the brightness of the sun across the entire spectrum, and you know the distance to it, and you know then if you can somehow derive the luminosity across the entire spectrum, then guess what? You can use that to find the distance to other stars, because if you can guess somehow their luminosity by hook or crook, maybe there's a way to do that. And there is. It's called spectroscopic parallax, but we'll talk about that later. So if you can get the luminosity of the star compared to the sun, or if you get the brightness of that star compared to the sun, then guess what? You can get the distance to the star. And that's called the luminosity distance, or the distance based on a standard object that you can calibrate against, and then get the distance based on how bright you see it to be, knowing how bright it actually is. And the standard way we talk about this in astronomy is using a thing called absolute magnitudes. And absolute magnitudes are a pretend concept that actually says, pretend you take every star or every object in the sky and move it close or far to a distance from the sun of 10 parsecs. 10 parsecs, 32.6 light years. And then how bright does it appear? What's its magnitude? Its visual magnitude, its V magnitude, its I magnitude. How bright does it appear when it's brought by magic or hook and crook or just imagination to 10 parsecs from home? And that is the definition of the absolute magnitude. So how can we use this? The brightness, we compare the brightness of the sun and luminosity, we can rearrange it and get to say, well, if we then say, let's look at one star, just one star, then if we think, when the star is far, it's dimmer than when it's near. And if but it's the same luminosity because it's the same star, so the brightness only depends upon the distance squared that we have. So the farther star, it will be compared to the distance of the nearest star squared, will give us, that will show us the distance between them. Remember, brightness is defined to be a difference in magnitudes. So we're going to use the magnitude system in order to get there. The brightness versus far is one thing, and then we can equate that to Pogson's equation for the magnitudes, and then we get the magnitude of the far star compared to the magnitude of the near star, and then that gives us the brightness difference, and we work out to this thing where we find that the difference in magnitudes is equal to a logarithm of the brightness. So a logarithm of the brightness gives a logarithm of the brightness, and therefore logarithm of the distance gives us the magnitudes. Now, if we can get the distances, we're good. But we've already established one thing. It's the same star. So the magic distance we're going to pretend it is 10 parsecs. So if we, instead of saying, look at the two magnitudes, we say one of them is the absolute magnitude, and that is the magnitude if the star were magically placed at 10 parsecs away. Then we end up with what's called the distance modulus equation, which says the apparent magnitude, and then you take the apparent magnitude, they subtract from it the absolute magnitude, and that is the same. That is equal to 5 times the base log 10 logarithm of the distance, and then minus some number 5. All right? Because remember, magnitudes have no units. They're really strange. They're just relative brightnesses between two stars. So they're a relative brightness, so they have no units, unlike luminosity, which does. So absolute magnitudes is kind of a funny thing. It's a unitless way of talking about luminosity. But if we know the distance of something, and we can measure the brightness in apparent magnitudes, then we have the absolute magnitude. And that's really something we can use. So absolute magnitudes are important. If we know the parallax of a star, the parallax is the inverse of the distance in arc seconds. So if we know the parallax, we can take the base 10 logarithm of the parallax, add 1 to it, multiply that by 5, and then add the apparent magnitude to that. We get the absolute magnitude. So now we take two measurable things, the apparent magnitude and the parallax, and then we do some magic, some mathematical magic, some arithmetic on that, and we get the absolute magnitude. So if we can get the absolute magnitude of a star, and know how that absolute magnitude compares to the luminosity of the star, and we have a fixed way of doing that, then measuring the apparent magnitude and the parallax will give us the absolute luminosity. There's a lot of trickery that goes into that last step, but it is possible, and it is doable at the very minimum. So as an example, if we take one of the nearest stars to us, actually not Proxima Centauri, but Alpha Centauri, which has a parallax of 742 milli-arc seconds, and it has an absolute magnitude of just a little bit brighter than 0, it's minus 0.01, then that means its absolute visual magnitude, apparent visual magnitude, meaning what we see it to be. It's a visual magnitude. And then the absolute visual magnitude is about 4.3, plus 4.3. And that's what the math works out to be. So magnitudes themselves are things that also we measure inside of filters. So a filter will actually determine it, what we use. So we can have a magnitude in the Johnson B, or the Johnson V, or the Johnson I, or the Sloan I, or the Sloan U, or the Sloan V, or the Sloan B. There's all sorts of things that you can measure it in, as long as you have a standard filter system. So absolute magnitudes are a really great way to actually get, a great way to actually give us luminosities. And roughly the solar luminosity in absolute magnitudes is about 5. It's recently been defined by the International Astronomical Union. And so absolute magnitude system no longer definitively relies on the sun, simply because the sun is slightly variable. So you don't want to try to tie an absolute system onto a variable thing, such as the sun. So roughly speaking, the sun is about an absolute luminosity of plus 5, give or take a little bit. And that corresponds to a solar luminosity of 1. So if we then go up and down, if it's 100 times the solar luminosity, then it has an absolute magnitude of 0. If it's 10,000 solar luminosities, then it has an absolute magnitude of minus 5. If it has 100th of a solar luminosity, then it is about an absolute magnitude of about 10. And if it is 10,000th, 1/10,000th of a solar luminosity, then it has an absolute magnitude of plus 15. So this kind of helps us kind of get around, because you'll notice that the luminosity, whereas the magnitude system is linear, the luminosity of the magnitude system is exponential. That's the nature of a logarithmic relationship. So that's how bright we can look at it. And it's another way of thinking about it. So brightness then becomes luminosity as long as we know the distance. And the best thing we can get for distance is called parallax. So parallax then gives us distances in parsecs, which is a geometric distance. So we can play lots of games and say, oh, if something's 20 parsecs away, what's the magnitude if you have an apparent magnitude of 4? And if it's like 5 distant parsecs away, the apparent magnitude of 4, what's the absolute magnitude, et cetera, et cetera. Lots of games you can play. So, and so what we find is that the relationships really lead us down a lot of different places. And we're going to use these relationships over and over and over again with respect to luminosity and brightness and magnitudes. And the distance modulus equation will come in many times in the future. So stay tuned, and we'll see you soon.